In this video, we're going to show how we can reduce the problem of ZOE to the problem of Hamiltonian cycles. So if you don't recall, the problem of ZOE is basically taking a matrix equation with zeros and ones only. So that equation might look like this. And I'm looking for a solution to this equation. So basically, values of a and b that have to be either 0 or 1, such that the solution to this equation is 1, 1, 1. One way you can think about that is I want to pick pick columns, so that in my columns that I've selected, there's exactly 1, 1 in each row. So for example, I could pick the first column and look at that, there's exactly 1, 1 in each row. But if I tried to pick both columns, I'd have 2 1s in the second row. That's too much. And if I only picked the second column, that would mean that I wouldn't have a 1 in the first or third row. So we're going to see that the solution here is going to be that a equals 1, b equals 0. But our goal is actually to turn this into a problem of Hamiltonian cycles. So what's a Hamiltonian cycle? Well, let's say we had a graph that looks like this. I'm going to draw it kind of silly. I want to find a cycle through this graph that passes through every vertex. So I could just go around the outside and that would do it. And we're going to add a certain property to this, but that's just what Hamiltonian cycle is. And what I'm going to tell you is that if I can solve this Hamiltonian cycle, which is it is a search problem, it is a problem in NP, because if I give you a cycle, it's very easy to check, does it go through all the vertices? And we're going to show that if you can solve Hamiltonian cycle, then we can also solve ZOE. And since ZOE is a NP complete problem, that would mean that Hamiltonian cycle is also NP complete. But what you notice here is that we've actually added this extra paired edges condition. And what that means is that I'm going to select pairs of edges, and I'm going to require that my Hamiltonian cycle only goes through one of those edges in each pair. We're going to get rid of that condition in the next video, but in this video we're going to have that condition here. So let's talk about how I can take a problem about matrices and turn it into a problem about cycles. And what we're going to do is I'm going to create a graph with two parts. On one side, I'm going to have a bunch of, I'm going to have a bunch of things representing variables, and on the other side, I'm going to have a bunch of things representing equations. So I'm going to do these in different colors. So let's put the variables in, we'll say blue. So I'm going to have, this is going to be a multi-graph. So there's going to be multiple edges between vertices. And by the end of this reduction, it won't be a multi-graph anymore. We'll have broken up things. But for right now, we're going to have a multi-graph. So for each variable, I'm going to create two vertices, and I'm going to have two edges going between those vertices. And in that case, since I have two variables here, a equals b, I'm going to be using this example. One of these edges will essentially represent setting a equal to 0, and the other will represent setting a equal to 1. Similarly, this will represent setting b equal to 0 and setting b equal to 1. And then we're going to have a whole bunch of edges representing our our equations. And for each row here, we are going to have one equation, or we're going to have one pair of vertices. So for this first equation, I'm going to have one edge, and I'm going to have an edge for each non-zero entry in there. So I'll have an edge representing that I have an A. I'm going to have two edges here representing that there's both an A and a B. I'm using A for the first column, B for the second column. that corresponds to the multiplication that we would end up doing to get this answer. So that's totally reasonable to do. So you can think of this as the A column and the B column. And then once again, I'll have another edge just with an A on it. And now that I have these, I'm going to link them all up into a big cycle. And this is the graph we're going to be working with, at least to start. So what this is eventually going to end up doing is when I find my Hamiltonian cycle, it's going to have to pass through exactly one of these two. That's not necessarily because of edge pair stuff. I haven't done anything with edge pairs yet. That's just because I need to go through each vertex once, except for the first and the last. And obviously if I take this edge and then I take it again, well, then I've gone to these vertices more times than I should. Or I've revisited this vertex when I still have a bunch of other stuff that I need to do first. So just by the nature of that, I am going to need to have to pick one of those and have to pick one of those and have to pick one of these and have to pick one of these and have to pick one of these. And that's actually pretty natural. So picking one of these represents choosing what my variable equals. And picking one of these is going to represent which variable equals 1 for that column, or for that for that row. For example, a Hamiltonian cycle would be something as easy as saying, let's choose A to equal 1. Let's choose B to equal 0. And then I'm going to go through all the edges labeled A. And that would give me a Hamiltonian cycle. Now, obviously there's a lot of Hamiltonian cycles, and not all of these are directly connected to solutions to this equation. So let's go ahead and add some restrictions that will more model the specific criteria of our problem. Because, for example, let's consider a bad Hamiltonian cycle where I secretly went through this A equals 0 edge, and maybe even this B equals 0 edge, but then I just stealthily took all the A edges anyways. That seems illegal. So let's make that illegal. Because, that would be a valid Hamiltonian cycle, but that wouldn't give me a solution to my equation. So let's make that illegal. And how we're going to do that is I'm going to add an edge pair for each, because what do we want to make sure happens? I want to make sure that I'm only going through A1, I'm only going through A here if I've set A equal to 1 here. In other words, I'm only going through A here if I haven't set A equal to 0. So what I'm going to do is I'm going to number all of these, just so we have names for these edges as we continue this problem. And I'm going to set edge pairs I'm going to take the A equals 0 term and put that in a pair with everything that has an A variable. So I'm going to have the edge pairs 1 and 8. I'm going to have the edge pairs 1 and 6. I'm going to have the edge pairs 1 and 5. So what do these edge pairs mean? Well, if I set A equals to 0, then if I look at these pairs so far, that means that if I'm using edge 1, I can't use edges 8, 6, or 5 in my Hamiltonian cycle. So I wouldn't be able to use those. On the other hand, if I set A equal to 1, then I'm not using the edge A equals 0. I'm not using the edge 1, which means that I actually have to use edges 8, 6, and 5 in my Hamiltonian cycle. Okay. So those are some of my pairs. Obviously, I'm also going to have a similar pair for where B equals 0 and the edge labeled that. Similar reasoning, if I set B equal to 0, then I have to use edge 3 and I can't use edge 7. But if I set the edge B equals to 1, then I'm not using edge 3 and I have to use edge 7. So before we do a valid Hamiltonian cycle here, let's do an invalid one just to look at it. Let's do a few invalid. Let's say that I set A equal to 0 and b equal to 0. So what happens? I keep going along my Hamiltonian cycle. And as soon as I get here, I say, uh-oh, I used the edge 1, which means I can't use the edge 5. And I'm stuck. I can't go any further than this. I can't go all the way around the cycle. So that's bad. So let's use a equals 1 instead. But let's still be bad. Let's use b equals 1, 2. That's not a solution. So I go here. I didn't use 1, so I have to use the edge 5. Now I didn't use 1, so I have to use the edge 6, but I also didn't use 3, so I have to use the edge 7. So somehow I have to use both of these edges, but then uh-oh, I did a loop-de-loop and I couldn't finish my Hamiltonian cycle. So now let's do it the right way. I'm going to set a equal to 1, and I'm going to set b equal to 0. And then when I go around this Hamiltonian cycle, I have to use the edge 5. I have to use the edge 6, and I can't use the edge 7. And then I have to use the edge 8. And I go ahead and finish my Hamiltonian cycle. And voila, we have essentially recorded a solution to this equation in this Hamiltonian cycle. So there you go. Even though these seem like very different problems, you can actually go ahead and turn this equation problem into a problem of taking Hamiltonian cycles with these certain paired edges. And what's the solution to my equation? How do I translate a solution here to a solution to my equation? Well, I'm going to look at what edges did I use here, and I'll write that in here. The edges used here tell me the solution to my equation. So there you go. That's how you can translate a matrix equation using zeros and ones into a Hamiltonian cycle with paired edges problem. And in the next video, we're going to talk about how to get rid of that paired edges condition.